everyone. My name is Martin Traverso. I'm here with David Phillips. We're both co-creators of Presto and currently CTOs at Starburst. In this presentation, we're going to talk about a bit of what's going on with the Presto project and the community. We're going to talk about some of the recent developments in the project and cover a little bit about the upcoming roadmap and features people are working on. And then we're also going to get into more details about support for Apache Iceberg within Presto, which is very relevant for data lakes. But before we get started, let's do a quick recap of what's Presto for those of you that may not be familiar with it. So Presto is a distributed query engine for data analytics. We built it from the ground up for speed and scale, and we've proven it in very large deployments at companies such as Facebook, which is where we incubated back in 2012, and over the years at many other companies that have adopted it. It's an open source project. We started the project back in 2012. We open sourced it in 2013. And it currently has a very, very large community of developers and users all over the world that are using it every single day. So unlike a traditional database, Presto separates the compute layer from the storage layer. And it does that via a pluggable architecture. It is extensible via connectors that allow Presto to query different storage backends. One of the advantages of separating compute and storage is that you can scale the compute and the storage layers independently. And this is super important for environments. For example, if you're running in a cloud environment and you need to be able to control your costs of your computation. You want to be able to shrink your clusters or scale them up as usage increases. And for example, if you're running, especially if you're running interactive queries, which might correlate with business hours in your company, you need to be able to shut down the computation or scale it down. So that separation allows you to do that kind of work. Presto can query data where it lives, so it allows you to take data from different data sources, read them into Presto as part of the query execution, join them together. You can join data from say Hive against MySQL. You can have say packed data inside Hive and rapidly changing dimension data in MySQL. You can query both at the same time. So that's one of the very, very powerful features of Presto, and one of the reasons it has become so popular in the industry. And finally, Presto can run anywhere. It can run on-premise. It can run in cloud environments and across different deployment strategies and different infrastructure. We designed Presto to be generally agnostic about the specific infrastructure it's running in, but you still have the option to be able to connect to the storage systems and the backends provided by different cloud providers. Presto has been adopted by all major industries. Since we open sourced it back in 2013, we've seen a large number of companies using it and adopting it over the years. We started with companies that were closer to what Facebook was doing at the time, like Netflix and large internet companies. But then over the years, many companies in different industries ended up picking it up, and you can see companies on in the retail industry, manufacturing, and even some companies in the financial industry, which was actually very surprising to us. Those companies tend to be more conservative about the technologies they take. These companies are all over the world. They are large and small, so there's a big community of users. Let's talk about some of the things that have been happening recently in the project. Let's talk about the community and how the project has been growing. So since 2019, the beginning of 2019, actually, we've seen tremendous growth in the size of the community, in the number of people involved, the number of companies using Presto, and also in the amount of development that has been happening. So as of now, we have about 2,800 people registered in the Presto Slack group, out of which more than 430 people are active every single week. And this involves people having discussions about development of Presto features, people seeking help, people that want to provide feedback, and or maybe they just want to say they need some feature or they have requirements that they would like the community to focus on. We've seen contributions from more than 400 contributors over the years, and this is contributions anywhere from code, like submitting a bug fix or new features, to helping other users, to people that have been writing blog posts, or helping spread the word about Presto. So it's a very, very large and vibrant community. And it's a global community. We have people all over the world involved in the project. Last year alone, we did conferences in 5 different parts of the world. We did a conference in India, one in Israel, one in Japan, and one in each of the U.S. coasts, in San Francisco and in New York. And each of the conference had an attendance of more than 150 people. So very, very strong local communities in different places. In the last year and a half or so, we've had about 5,800 commits in the project, and that's more than 25% of all the commits in the history of the project. So we've seen an acceleration in the amount of work and contributions that are happening. So it's a very rapidly changing project. In that period, we've done 44 releases. We tend to release about every 1 to 2 weeks. So, like if you want to be on the bleeding edge, like you can keep up with and keep track of those releases. There's always new features coming up. So in that period, we also implemented a large number of features, all the way from language improvements to performance improvements. We made the query engine smarter and better. And we've also added a bunch of security-related features, from fixing issues to fixing security issues to adding more advanced security schemes and functionality. So I'm not going to go into details about all of these right now. There's more you can see in that link on the bottom of the slide. And in a bit, we're going to talk about some of these recent developments. So on the connector front, we had also a dramatic growth in the number of connectors that we support. We've already had a pretty good list. And over the past year and a half, we added connectors, for example, for Elasticsearch, for a number of open source projects like Apache Phoenix, Iceberg, Druid, and Pinot. And then even for some commercial systems like BigQuery or Google Sheets or Oracle. So let's dive into some of the recent, these are changes over the last few months. They happened over the last few months that are very important. They have potentially a very big impact on the experience using Presto. So the first one is support for variable precision temporal types. So historically, Presto has been able to support temporal types like timestamp with time zone, time, and so on. But it only supported millisecond precision, and that can be very limiting, and especially when like dealing with data sources that support temporal types with higher precision. Like for example, Oracle deals with microsecond precision, so not being able to support that makes for some cumbersome transformations. You can lose precision when dealing with data from different systems, and also limits the usability of the system. So in the past few releases, we added support for variable precision down to picoseconds. So that makes it easier to map these types in Presto to external systems, and also is very important for some use cases. Like for example, in the financial sector, it's not uncommon to have to deal with data that has precision in the nanosecond range. So being able to operate on that data is super important for that companies in that industry. We also added, I'm going to talk about three features that are related to performance. The first one is being able to push down complex operations into connectors. So the idea here is Presto can, for connectors that are more sophisticated, like a connector for a RDBMS or a connector for something like Apache Druid or Pinot, where they actually have a query engine with that manages internal optimized data structures. The idea is to be able to push down part of the computation of a query into those systems to a couple of reasons. One is the queries can perform much better because those systems may be able to take advantage of their internal data structures or algorithms to be able to process that data more efficiently. And second, it avoids transferring data across the network into the Presto process and having to process all that data inside the Presto engine. So we used to support push down of simple operations like filters, very simple filters, but we've been extending that to support things like aggregations, top end operations, limits, table sample, and so on. There's the support is across different connectors is not uniform. So some connectors have better support for that than others, but it's one of the areas that keeps evolving. It's just something that's now allowed and supported by the engine, so connectors can start taking advantage of that functionality. The second performance improvement is a feature we call dynamic filtering. This is a feature that can dramatically improve the performance of queries that involve joins across different tables. And it works by getting information about what data is actually being considered for a join from one of the tables after all filtering and transformation has been done, and using that to do early filtering and pruning of the other table that participates in the join. And this is something that it's possible to do at runtime, but it may not be possible to do at planning time. So this adds an additional capability that can make queries that previously had to scan a lot of data be able to prune that data very, very efficiently, very quickly. And this is particularly useful when running queries against data sources like Hive that have a notion of partitioning. So it can take advantage of what it finds from one of the tables to prune the partitions of the other table dynamically at runtime. And then the third feature we've added related to performance is storage level caching within the Hive connector. This allows the connector to cache files from S3 or HDFS or Azure storage or GCS, Google storage, GCS, into local storage in the Presto machines. And this can help reduce latency and reduce network transfers when querying data from tables in those storage systems. And finally, one big area where we've been doing a lot of work is security. So this is one of the aspects is web UI security. Previously, the web UI inside the Presto coordinator was unsecured. There was no authorization or authentication. So now that's protected behind authorization and authentication. All the information about queries is also protected with authorization policies. And we've also secured all the APIs that expose any information about queries. And all the APIs or any endpoint, network accessible endpoint in Presto clusters are now secure. So now you can have a lot more confidence in that Presto cluster will be able to operate in a more secure manner. Let's talk about the roadmap of features that are coming up in Presto. So one of the things to keep in mind is that the Presto roadmap, because Presto is a community-driven open source project, is driven by what people are willing to invest time in and have passion about working in. So let's talk about some of the items that people have expressed interest in working on or actually actively working on right now. So we're going to talk about three areas. The first one is performance. One of the project that we're starting to look into is revamping the Parquet reader. The current reader, after running some tests, we found out that it's not as efficient as the ORC reader. It can, in fact, be up to 5 times slower than the ORC reader. We think we can do much better than that, and we're starting to look at it. So after we're done with this, we should be able to bring the performance of the Parquet reader close to what we can achieve with ORC. And given that Parquet is one of the most prevalent formats out there, it's super important to go ahead with this. This work will also allow us to take advantage of some of the more advanced features in the recent revisions of Parquet, like page indexes. It's something that can further help optimize the performance by pruning data that doesn't need to be read. The second area we're working on is revamping the client protocol. So the protocol right now is a single-threaded, single-stream protocol. It's not optimized for downloading a lot of data from Presto, which it hasn't traditionally been the use case for Presto, but we've seen people asking for that over the years. So one of the things we're focusing on is making the protocol more efficient by coming up with a much better on-the-wire representation of the data, and then also making the protocol parallel, which should make it easier and more efficient for systems that are inherently parallel to be able to fetch data in bulk from Presto. And the final performance change we're looking into is support for materialized views. This is not an internal performance improvement. This is a user-facing feature. Materialized views are kind of a hybrid between a view and a table. It's like a view that the engine can process and can store the results of the view and maintain the results as the underlying data sources change. So the idea is that you can define one of these materialized views. The engine will compute the results, store it, and then if you query the materialized view again, it doesn't need to recompute it. It can just access that data from the storage. And then there are protocols to be able to know when the underlying sources change, and then the materialized view needs to be recomputed. And we're working on ways to do that computation incrementally. So this is akin to the feature supported by other databases like Postgres and Oracle support this. Over time, the idea is to make the engine smarter about materialized views and be able to take advantage of the view definition and the contents of what's pre-computed to be able to satisfy other queries, like by doing a partial rewrite of subsets of the query plan. So instead of having to recompute those entire plans every single time, you can take advantage of stored data. Right. The second area is a set of features that improve the flexibility and the power of Presto as a platform. So the first one is support for complex Hive views. If you're not familiar with Hive views, the views are defined in using Hive query language, which is not necessarily compatible with Presto. Like for simple views, it can be syntactically similar, sometimes even semantically similar. But as you start using more complex features from Hive, the syntax is different from Presto, and the semantics, moreover, can be different. When you're running Presto against a Hive metastore, especially when people are running a mixed environment like that uses Hive and Presto, you may encounter those type of views, and Presto can't query them. It can't look at the view definition and make sense of it. So this project is about adding support for those complex views by doing an on-the-fly translation between the Hive view and Presto query language. So the idea is that when a user queries a Hive view, Presto takes the view definition from Hive, translates it using a semantically appropriate translation, and then execute that view as if it were a Presto query under the covers. So it's fully transparent for users, and you should just make it much easier for people that are running in mixed environments and or people are trying to migrate from Hive into Presto and they don't want to go through a manual process of migrating all the views. The second area is a revamp of the way Presto manages functions, and this is how it manages function registration and resolution. So currently, functions are defined statically when the server starts. So they are part of the code base, part of plugins in the code base. So once the server starts, it discovers all these functions, and those are available for the lifetime of the Presto process. And this has been the way it's worked for the past few years, but it's very inflexible. So what we're doing here is we're extending the connector APIs to allow connectors to be able to participate in function resolution, resolve the functions, and provide implementation of the functions at runtime dynamically. So this makes it possible to, for example, you can have a connector that can manage the function library externally and do it dynamically by, I know you might be registering the function might be registering some other database or repository, and they can be updated by the connector and provided to the engine dynamically without having to restart the Presto cluster. This also opens up the door for more advanced functionality, which we're looking into, like, for example, true user-defined functions, where users can define the body of a function using a part of this. It's a procedural language that's part of the SQL standard that allows the users to define simple procedure that involve control flow statements and so on, and potentially in the future things like being able to support languages like JavaScript or Python or anything that can be properly sandboxed within the Presto process. All right, and in terms of connectors, there's a few connectors in flight right now. There are pull requests for all the three of these. So there's a connector for Salesforce, for ClickHouse, and for Snowflake. The Snowflake connector is about to go in. The other ones are in review, but they should be hopefully in the next couple months or so. Okay, so I mentioned before David was going to get into a bit more into Apache Iceberg. Iceberg is one of the most exciting recent technologies to support data lakes, and we recently added some support for it in Presto. So David will take care of that.
Thank you, Martin. We're going to talk today about Apache Iceberg. Since this is a data lake summit, Apache Iceberg is one of the most interesting and promising technologies that can transform the way that you use data lakes. So Apache Iceberg is a new table format. It deals with how data in tables is tracked on disk, like both the data in the tables and the metadata about the data, like the data files. It's not a new file format. It still uses Orac or Parquet or Avro on disk, but the higher level metadata around the way that the data is written and the way that the data and metadata is organized is what Iceberg tracks. So Iceberg is an alternative to Hive tables. Iceberg can live side by side with Hive, but it manages all the metadata for tables. So instead of having like stored formats and partitions all stored in the Hive metastore, that's all taken over by Apache Iceberg. Iceberg is a community standard. It has a full specification, which is a nice change from Hive, which is just kind of like an ad hoc specification that everyone sort of kind of adheres to, more or less, whereas like Iceberg is a very well-specified project, so that hopefully all the implementations will be very standard. And it was originally from Netflix. They've been using it in production for quite a while, and it's now a top-level Apache project with a big and active community behind it. So why Iceberg? Like, what problems does it solve over Hive? Iceberg has full support for schema evolution. You can add, drop, rename, and reorder columns in a table, things that are difficult to do in Hive, and we'll get into that later. It has, unlike Hive, which has explicit partitioning, Iceberg has hidden partitioning. So you can have a timestamp column in your table, and you can say, I want to partition that table by day without having a separate day column in the table that users have to know about. It's able to evolve partition specifications. So you can start off, maybe you partition your data by month, and then you later partition it by day. And it doesn't affect any queries, and it doesn't affect any of the existing data. So that partition evolution is completely transparent to anyone using the table. It keeps track of old versions of the table, allowing you to do time travel queries. You can say, let me query the data in the table how it looked a day ago or a week ago, which is useful if you're trying to debug a bad data load, or maybe you've got like a machine learning data set and you want to compare how it looked yesterday. There's a lot of use cases for that. Along with time travel, you can also roll back to the data. So if you loaded some bad data, you can go and look at the data between today and yesterday and say, oops, we need to roll back to yesterday's data and then reload it. And Iceberg makes that very easy. Iceberg works better than Hive tables on cloud storage systems like S3. It was natively designed to work well with storage systems, whereas like Hive was designed back in the Hadoop days where you had HDFS. HDFS had some pretty strong file system guarantees that you don't have in the cloud storage systems. And so Iceberg was designed to work better with those. Iceberg is much faster to scan plans. When you're starting a query, you need to figure out where's all the data. Iceberg, you can do that faster because of the way the metadata is laid out, which we'll get into. And also it keeps track of statistics, and it guarantees that the statistics are correct so that you can do better data filtering and produce better query plans. You can decide what types of joins and join ordering when you're planning the query that is difficult or impossible to do in Hive, like if you don't have statistics, whereas in Iceberg, you know the statistics are always there, so you're going to get better query plans. It supports serializable isolation so that people can be reading the table and they get consistent results while people are also writing to the table. So nobody ever sees inconsistent results or partial results while they're doing reads. And changes to the table are always applied atomically. They're applied all at once. And Iceberg also allows multiple concurrent writers to the table in a safe manner. So maybe you have like multiple ingest streams, or you've got like a data stream coming in from Kafka, and you've got someone doing a batch insert. Both of those can work at the same time. So a bit about why Iceberg is better. We can talk about what Hive does. So Hive tables, when you're partitioning, they have separate partition columns. You say, I want to partition on this column. The partition, and it's treated as it's a separate, completely separate column. You can only partition on values in Hive. So if you want to partition on a date, you actually have to have a date column in the table with just a date, no time portion. Whereas, like, usually when you've got events, you've got a timestamp associated with that event. Well, in the Hive table, you've got to have your timestamp column, and you've got to have the date column separately. And then users have to know that, well, filtering on the time column doesn't give you any partition printing. You have to filter on the time column and the date column. And we'll see how Iceberg improves on that. Partitions in a table are collections of files. And so you can think of a Hive table, each partition being like a directory full of files. And so each partition has a separate directory in the file system. When you're going to go and read that partition, you have to scan the directory to find all the files. And so if you've got a table with 1,000 partitions that you're going to read, you've got to do 1,000 directory listings. And those directory listings can be slow on cloud storage systems or even on busy HDFS systems. And so it's best if you can avoid doing directory listings. And you also have the problem that on S3 in particular, S3 is eventually consistent. So if you write data into S3 and then you go and list the directory, you might not actually see the files. So somebody can do an insert into the table, and then someone else goes and reads it, and they'll either miss some or all of the data that was just inserted. So that leads to inconsistent results for readers. Maybe somebody just inserted data for yesterday, and then you go to read it, and you only see half of the data for yesterday, and you get a bad result. Another thing is how Hive maps the metadata about the tables to the files on disk. So when you have a column in a table, you need to know, how do I find this column in the data file on disk? So for traditional formats like text files, they're effectively like comma separated values or CSV files, like you'd have in Excel, where they're mapped by position. And so with this scheme, you can't remove or reorder columns, because in the middle, you can't do that in the middle of the table, because that will mess up all of the existing data files. Because now, if you think of like you have a CSV file and you just delete one of the rows in the header, well, now all the data columns don't match up and you're going to be reading the wrong data. So newer formats like Orc and Parquet use column names, where the column names are stored in the data files. And that works a little bit better, because now you can reorder things, or you can add or remove columns because it's by name, but you can't rename a column. Because if you rename a column in the metastore, now you don't know how to access that column in the existing data files. Or even worse, maybe you do a rename a couple of times, and now you're reading a column that used to be a different logical column, and now you're reading the wrong results. Iceberg tables are a collection of snapshots. Snapshots are the full state of the table, including all the data and the metadata. A snapshot is immutable. So once you do an insert into an Iceberg table, you get a new snapshot representing the new state of that table. And that snapshot has an identifier, and that snapshot is immutable. So every time you insert into the table, you get a new snapshot. And the old snapshots are never changed, and they're still available, at least until they're cleaned up or garbage collected. So readers always are reading a specific snapshot. So readers always see a consistent view, because once a snapshot is created, it never changes. And that's what allows readers to have serializable isolation. And then writers are always producing new snapshots into that table, which are immutable. Unlike Hive, which heavily relies on the metastore to store information about the table schema and the partitions and the statistics, all of the metadata for Iceberg is stored in a file or a collection of files rather than in the metastore. So the metastore usage for Iceberg is actually very simple. The metastore simply says this table name points to this file system location containing the snapshot with all of the manifest files. So this means that you never have to list directories or make a bunch of RPC calls to the metastore, because it's all stored in these data files. So the partition manifest files contain the full list of the data files, and thus we avoid directory listings on S3 or on HDFS or whatever storage system you're using. To plan a query, all you have to do is read the manifest file, and then you get the list of all the data files. The metadata files also contain statistics that are guaranteed to be correct, because they were written at the time that the data was written, so that you can rely on them to plan queries or prune data. And that leads to better query plans and less data to read. Unlike in Hive, where Hive statistics are optional, and sometimes because Hive allows or sometimes encourages people to go mess around with files directly on disk, the statistics stored in the metastore can get out of date with the files that are on disk. So you can't always rely on them. So as we talked about, Hive uses explicit partitioning, whereas Iceberg uses hidden partitioning. So in Iceberg, you say, I've got my data columns, and then to create a partition, you declare it as a transformation of one or more of the data columns. So you can do simple value or identity-based partitioning like in Hive, where say you've got a string column and that each unique string is a partition. You can also do various transformations, like you can transform a timestamp, like you can partition it by hour, by day, month, or year. You can transform numbers or strings, or I think any type, into a fixed number of buckets by hashing it. So that's similar to bucketing in Hive. But with Iceberg, it's all rolled into partitioning. There's also numeric transformations where you could say take a number and partition it on the value divided by 100. So you end up with fewer partitions and you have unique numbers. And there's some interesting use cases for that. So the important thing is that users using the table don't need to know about partitioning. They just write their normal query with a normal where clause, filtering on the original column, and then Iceberg will do the right thing and use the partition to filter the data. And as we mentioned, the partitioning can change. So you can start with less granular partitioning by month and then switch to day, or you could do vice versa. Maybe you end up not having as data as you think, and it's too expensive to have hourly or daily partitions, and you can switch it to a higher granularity. And this is all completely transparent to both readers of the table and writers of the table. Nobody actually has to be aware of what the partition columns are or how it's declared. So Iceberg is fully supported in Presto as of a couple releases ago. You can read and write to Iceberg tables in Presto, including create table, drop table, insert, everything you'd expect. It all just works. It's compatible with Spark or any other Iceberg implementation that follows the Iceberg specification. It currently supports ORC and it supports ORC and Parquet files on disk. There's a pull request in progress to add Iceberg support. Although one of the nice things about Iceberg is that you actually don't need to care about what the physical file format on disk is. So the fact that like you've got files that are Orca Parquet, that's actually really an implementation detail that no one has to be aware of because everyone's going through the Iceberg interface. So Iceberg abstracts that a lot compared to Hive. And in Presto, the Iceberg connector supports has the same metastore and file system support as the Hive connector. So Presto has support for like thrift and glue metastores. It supports like HDFS and S3 and Azure and GCS and other file system storage format or other types of file systems. And like for HDFS, it has support for Kerberos security and encryption and other various features like that. All the things that have been added to the Hive connector over the years for those systems, those are all completely supported in Iceberg. So it's pretty easy to move your existing workload from Hive over to Iceberg. And you can do that in an incremental manner. And we've got some upcoming work to make it even easier to migrate transparently from Hive to Iceberg. So thanks for joining our talk. And it's been good to tell you about all the things that have been added to Presto recently and about Apache Iceberg. We hope you join us on the Presto Slack. You can see the URL on the slide. This Presto Slack community is very active. There's people on there from many countries around the world, people on there in all time zones. So you can post a question at pretty much any time of the day and get an answer very quickly. And we hope to see you there.